Okay, so all the exams should be graded now. I don't know if I'll get to today. I have some exams from other sections. I'm trying to kind of prioritize those. But by the end of the week, that third Excel assignment will be graded as well. And you kind of get a good idea of kind of where you're at grade-wise once that's factored in. We will just kind of mention, I will post an online quiz after today's class that will be due before Friday. I will also kind of put up the next individual assignment. So the very first part of it, you'll all be using kind of the same data set, and then the latter part of it, you use whatever your individual data set is. Now that second part, we really won't cover probably until sometime next week. I'm guessing Wednesday maybe. But that first part is kind of what we're going to be covering today. Right? So it's that kind of the general kind of data set for the first problem. You'll all be using the same one. That we can start working on kind of after today's class, and then the latter part will you can slowly start working on that as we continue to cover material. Okay. I'll also be posting a Connect assignment, and I'll probably just get it up there, but we really won't be able to start working on that until definitely after Friday's class, and then kind of as we cover material next week, you'll be able to kind of chip away at that a little bit as well. Okay. But I just want to get them up there so you can kind of work on them early as we cover the material. Also, I did re-upload kind of the slides for this week, kind of threw in a couple different things and rearranged things a little bit. So if you had printed it off prior, you might be missing a slide or two, or it might kind of be a little bit out of order, but it should be pretty close. But those are up on Canvas now. Any questions for me before we kind of get going into things here? Okay, so we left off last class starting to think about, all right, we've done all these different types of tests for the differences between populations, even like the matched pairs kind of difference between time periods or different variables. So what if we had multiple populations and we wanted to see whether or not kind of the mean is different across several groups, right? So we kind of left off some of the assumptions that we need. We need the populations to be normally distributed. We need standard deviations to be equal, and we need to have kind of independent samples, right? Now, these are likely hard for us to get, but if we did have this scenario, we could do some ANOVA testing. So our hypothesis test was always going to be essentially that we assume that every group has the exact same population mean up to however many groups we have, kind of C. And then the alternative hypothesis, we're trying to test for whether or not they are different, right? So if they're not equal to each other. So it's the same kind of thing we were doing before when we were looking at the differences between two sample means. It's just now we've got a bunch more, right? So we could think about what would it look like if the null hypothesis was true? Well, if we take samples, right, even if the null was true and that they all have the exact same population mean, so they'd all be coming from the same distribution, right? Well, it's very likely we could see sample means from here and here and here and here, and they would be different, right? These based on the samples, it looks like there are differences across groups. However, even if they're coming from that same distribution, centered around that same population mean, well, it's very likely we see sample means that are a little bit different, right? But how different do they have to become, right, in order for us to be able to kind of reject this assumption, right? Because it very well could be if we see sample means that are much further away from each other, right? So notice here, now the sample mean we see for group 4 and group 1, there's a much wider gap. So if the alternative hypothesis is true, well, if I saw this, right, as my sample mean, it's way more likely that it's coming from kind of this blue distribution than if it came from that purple distribution, right? I mean, if you think about p-values, right, the area to the left, if we do a left-tailed test, or two-tailed test, we have to multiply by 2, but the area to the left of this sample mean, if it was coming from the purple distribution, is essentially 0. Well, if we look at the area to the left, if it came from that blue distribution, is, at least we can see it now, right? At least it would be, if we shaded this in, it would look like it existed, right? So if the alternative hypothesis is true, it would mean that, yeah, it's more likely when I see sample means that are further apart, that they're actually coming from different distributions, right? But how can I tell whether or not, how far apart is far enough, right? How far away do these sample means need to be from each other for this null hypothesis not to be true? So what we're going to do, right, is we're going to have, even if we had different sample sizes, even if we have the same standard deviation, different sample sizes, right? I drew all of these distributions for the sample means as though they all had the same variance or the same standard deviation. But we know, right, that the standard deviation of whatever group we're looking at, 1 through 4, right, depends on kind of the sample sizes of whatever group we're looking at, right? So we know the sample size is going to influence that standard deviation, so we need to take that into consideration as well. So what we're going to first do with this ANOVA testing is compute the differences between the sample means. We're then going to get the variation of each sample, or the kind of the sample variance for each one of these samples that we have. We're then going to use a ratio, which essentially is looking at the variance within each group, right? So let's say we want to know if the mean, I don't know, miles per gallon varies across different car companies, right? Ford, GM, Toyota. We're going to have some variation across those different kind of car makers. But also, if we look at, Toyota makes several different cars, we're also going to have variation within each one of those groups or within each one of those companies. So we're going to take a ratio of those two variations, and it's going to give us a test statistic, which is going to be a F statistic. So it's going to be coming from this F distribution. So Y, if I can get here real quick, I'm going to go, let me see where I eventually have it. I'll go back through this. Eventually, we're going to get this F statistic, right? So it's kind of this ratio of between, right? So across, you can think about this word as between, right? Across the different car companies, divided by kind of this within treatment or within group. So the variation within each car company. Now, if these are measures of variation or variance, variances always have to be what? They're always greater than variances have to be what? There's one value a variance has to be greater than. Can the variance which of these couldn't it be? Yeah, right? Variances are always positive, right? Standard deviations are always positive, right? So if these are measures of variance, we know that this F statistic will always be positive, right? So this F statistic we're going to eventually find will always be positive, and it's somehow representing to us the amount of variation we see across the treatments relative to kind of the variation we see within, right? All right, so we'll get back to that again. I just want to kind of connect that before we start working through these examples. So I'm going to go through quite a few slides, and I'm going to go through them pretty quick because I'm not going to have you ever do this by hand. I'll show you what the equations look like just to set up so we can kind of interpret the results a little bit better. And then I'm going to show you how we use Excel because that's how we're going to do this in practice. So what we're first going to do is think about, okay, I'll use the car company one, right? There's going to be, if I had every single car from every single car company, there would be an overall average miles per gallon, right? Across every different type of car and every make and model, so to speak. I'm going to calculate that, and then for each group, I'm going to say, okay, what is the average miles per gallon from Ford? What's the difference between the Ford's average miles per gallon and every car maker's miles per gallon? So I'm essentially looking at how does each car company's average miles per gallon vary from kind of this overall kind of like sample, this overall average across every single car company. Excuse me. I'm then going to weight that, right, by how large the sample I had was from each one of these car companies, right? So it's kind of like, you can almost think about this as like a weighted variance, because then we eventually, if we think about when we were doing this before, N is our weight now, but we're still looking at the deviation from some kind of like overarching mean, right? So once we compute this, we then have to divide it by, well, instead of dividing it by kind of N now, this kind of looked across the different groups, so we'll divide it by the number of kind of groups minus 1. So C is going to represent the number of groups we have here, or the number of car makers or car companies we have here. Okay? So that kind of gives us our numerator. This is measuring how much variation was there from that kind of overall average from each one of these car companies, right? Each individual kind of maker, right? So we can kind of think about an example. I could kind of use some actual values instead of doing car makers. Let's say I want to know if the average kind of varies across the courses, some of the different courses I teach. So here's my sports econ, here's kind of principles of micro, and then kind of statistics, right? Business statistics. I have kind of the average grade across those. Maybe I think this was from like one semester. And then I kind of have the standard deviations, and I have my sample sizes, right? So I had quite a few more students in business stats than I did kind of these other two. So what I'm going to do is I'm first going to calculate kind of this overall average. Well, if I know the average from each group, and I know the sample size from each group, essentially that's just going to be kind of like a weighted mean, right? So I'll take each group's average, multiply it by the sample size I had for that group. That will give me this kind of overall, this X bar of this like average across all my classes, right? Once I have that, all right, so I kind of have this overall average, I will then have to, sorry, not this overall average. Once I kind of use this weighting, I have to still turn it into an average by dividing the total number of students that I had, right? So NT here would be if I added up all the students I have across the classes, right? So I can do that, and I get kind of the overall average was about a 79, okay, across these three courses. I then want to say, okay, how much does each one of these courses means vary from that overall average, right? So this one isn't very far from that, what, overall average of 79.7, but this one is quite a bit above it. This one's a little bit below it, okay? So I'll then look at the deviation of each group's means from that overall mean. So that's what I did. You know, the first group, not very far away, weight it by the sample size I had for that group. The second one, a little bit below it, but, you know, weight it by the group, you know, the number of students I had in that class. This one, quite a bit further from that mean, weight it by the number of students. And I kind of get, you know, SSRT, you don't have to worry, SSTR, don't worry too much about what this stands for. This is you know, kind of a placeholder for us. Think about it just as notation. We then divided that by the number of groups that we were looking at the deviation, you know, from that overall mean. So we had 3 groups, so 3 minus 1, and we get this MSTR, right? This is going to be what measures kind of the variation that we saw across these groups or across these different classes. So that's going to be that numerator of that F statistic, okay? We then are going to look and say, okay, what's the within variance of each group? Well, we can calculate the sample variance for each one of those classes, right? If I had the actual like 61 students, I can calculate the sample variance across those 61 students in those business stats courses. I then weight that by kind of n minus 1, right? Because this is a sample. I'll then eventually kind of divide by the total number of students I had minus the number of groups. Like I said, I'm not going to go into exactly why these formulas are what they are. I'm just giving you a little bit of background before we get to the interpretation part. I now have this MSC, which was measuring how much variation there was within each one of these samples. Not across them, but like within each one. So this will be my denominator of that F distribution, or of that F statistic, okay? So we could plug our numbers in there, get that value. We then kind of finally get to that F statistic equation, which is once you have that between kind of group variance and that within group variance, you take the ratio of the two. The F distribution is a little wacky. I'm not going to make you use the F tables. They're not overly fun to deal with. You've got 2 different degrees of freedom, which are kind of your number of groups minus 1 and the total number of observations across all groups minus the number of groups you have. You could look at the probability density function and say, holy hell, I don't want to deal with this thing at all. But we really don't have to, right? So the F distribution, kind of notice, right, we're always going to have positive values, right? Because you're taking a standard deviation divided by a standard deviation or a variance divided by variance. They're always positive. Positive divided by positive, going to be a positive, right? Okay, so you can kind of see as our degrees of freedoms get higher, right, we get this F distribution that starts to look, I mean, I wouldn't say it looks normally distributed, but at least it has kind of like, almost like a normal distribution with a really long right tail, right? So this F distribution, no matter what your degrees of freedoms would be, is always kind of right skewed, right? So once we get to that example, if I use those values I calculated, my F-stat would be 2.79. I could look at my 2 degrees of freedoms there, go to my F table, look up the critical values, and then it's the same thing. Once I have critical values in my F statistic, it's still test statistic, just comes from the F distribution. Well, is it more extreme or larger in absolute value than 3? No, so I would fail to reject the null at the 95% level, but I could reject the null at the, what, 90% level? Right? So once we get to this point, it's really the same thing we were doing with hypothesis testing before. We can compare critical values to that test statistic. So with 90% confidence, I could say that there is variation across the groups or across my classes, right, in terms of the average grade I was seeing. But with 95% certainty, I couldn't say that there's any differences in the means across, or the, sorry, in the like average scores across my classes, right? So, you know, I guess that's a good thing, right? With 95% certainty, I really can't reject the null, which is that, you know, my classes kind of have generally the kind of the same average, right? Based off the sample evidence that I had, okay? So that's kind of what we're doing, but I'm never going to make you do all this math, right? So I'm going to show you how to do this in Excel. So I have kind of these steps of how you would do this, something I'm going to show you in just a second. So you can always go back and revisit these. It lines them up kind of, you know, step by step how to get this thing that we'll need for ANOVA testing, but also something we're going to need for linear regression moving forward, right, when it comes to Excel. So I have this ANOVA file, right? It just says ANOVA on Canvas. Let's just double check. I'm pretty sure I put that up there. I'd hate to tell you that and then not be there. Yeah, right there, right? ANOVA, okay? So let's go to the sheet that says ANOVA, right? So I've actually been pretty good about not using a lot of sporting examples, so I figured I'd do one today. Although it kind of applies to, you know, non-sports as well. So I've got 3 different football conferences, right? And I have all the teams in those conferences. I have what their average kind of attendance was, okay? So what I can do is go to, all right, I forgot. I have to show you. It's already on this computer. So I go to File, right? I go down here to Options. I then go to Add-ins. Now, if you're on a Mac, when you pull up Options, it looks a little different than this, doesn't it? Is anyone on a Mac in here? So if you go File, Options, it won't look exactly like what I have right here, but there should be somewhere, I forget exactly where it's at, there should be something that says kind of Add-ins, okay? So I click on Add-ins. I then kind of see this, and it says, okay, here's all these different add-ins that are inactive and some active ones. Go down here to where it says manage your add-ins. That should automatically be selected. There's some other options here. We're not going to use any of that. It usually should be defaulted to those Excel add-ins. Hit the go button, and you'll see typically there's like 4 options here, right? The one we want is this analysis tool pack, not the -VBA one. Okay? So I'm going to hit OK on that. Now, it doesn't look like anything changed, but if I now go to the Data tab, I should have this data analysis kind of there. Now, I think, you know, usually the default is that it's not turned on. It might have already been there for some of you. If you go on a computer, it might already be under the Data tab. Kind of one of the nice things about me doing this on my laptop is like that one gets wiped every night, and so every time I open Excel on the computer over here, I have to literally do this get this add in every single time. But once you do it once on that computer, you're good. Okay? Any questions on that? Anyone having difficulty finding that? If you've got a Mac, or let's see if there's anyone in the chat. Okay. So like I said, those steps are kind of right here as well. So if you're kind of doing this after the fact, and I don't know, you're on a different computer, here's kind of a reminder of what those steps are. Right? So I've got these different average attendances for these 3 different conferences. I might want to say, well, is there differences across these conferences, right? I don't know, is the average attendance in the Big Ten games, different than SEC games, right? I might think that's true. So what I'll do is I'll go to this data analysis button here that's under the data tab now. Here, I'm going to cancel for a second because I realize if I'm having trouble reading this on my screen, you guys are probably having a little bit of trouble reading on there. So go to data, data analysis, all the way up at the top. So it might show up here, go all the way up at the top, there's this single factor ANOVA, okay? So single factor, we're just looking for variation across one factor, right? Which is the different conferences, okay? So I hit okay. What's my input range? So I'll click on this arrow button, and now I can select what I want it to use. So I'm gonna select the labels here, and then go down and select all of my data, right? Now you actually could, if you wanted to, because there's no data to the left and right, Control-Shift, hit the over arrow, or Command-Shift, hit the over arrow if you're on a Mac, and then the down arrow. But notice, it stops when it hits a blank cell. But if I then just hold Shift, I can kind of go down 2 more. But this is a pretty small data set. It's pretty easy to kind of select everything. So I then hit this little guy there, and it sends me back to this helpful little kind of interface. So it asks, how are these grouped, right? Any data set I'm going to give you, I'll group it by rows, right? So, or sorry, not by rows. I'll group it by columns, right? I should never have kind of a data set for me where it's grouped by rows, right? So when it says group by columns, each column represents a different group. If you have this group by rows, it would be like Big Ten and then kind of written out, horizontally. Most data sets don't look like that. So I'm sure there's a reason. I'm sure there's some examples where we'll have data like that, and that's why the rows option is there. But for us, I always kind of give you the data in these nice columns, right? Now I have to make sure I did select the labels here. So I have to make sure I select this button that asks me if the labels were the first row of what I selected for the input. That way, if I don't select that, it treats them as, first of all, it'll either give me an error. I can't remember if ANOVA, if it gives you an error or not. But once we get to linear regression, if we accidentally don't select that labels button, it treats it as a number, like converts this alphanumeric value and uses it as a number. We don't want to do that. So we have labels in the first row. I'll just use my alpha of 0.05 here. So I'll just test this at the 95% level. I could change this if I wanted to testing at the 99% level, right? Alpha of 0.01 or really whatever I want, okay? Now, you can put this on the same worksheet. I don't know if you guys have had how much familiarity you have in Excel, but right, if I select output range, I can then select what cell I want it to kind of start in. I could say, okay, I want it to put the output of this ANOVA starting here and go this way. Right? I typically don't use that. It's probably better to consolidate things, but I'm much more of a fan of just putting it on a new worksheet. Right? So this new worksheet will just create a new sheet down here, which will have my results. Okay. All right, so hit OK here, and I get all kind of this output from Excel. Okay? So what does this output mean? How do I use it? How do I make effective statements with it? First thing I usually do is make sure I can just kind of see that whole first column. I'm going to rename this here. So ANOVA output. Right. So I've got a bunch of things up here. Now notice it really is showing me kind of some of the intermediate steps. So it's showing me the different averages and the different variances and the different sample sizes that Excel is using to essentially do all the math that I was showing you in those slides I told you I'll never make you do, right? I then look down here. So I'm going to use this between groups, right? I'm going to look here at the p-value, and now it just becomes the same rejection decision we've always had. Is the p-value less than alpha, right? If the p-value is less than alpha, we can reject the null. Right? Well, here we clearly have a p-value that's not going to be less than alpha. Our alpha was what, 0.05, right? So this is not even close to being less than point. So I failed to reject the null. Now remember, the null is that the means were equal across these groups. or that kind of the average attendance was the same across these conferences. So based on the sample evidence I found, I think this is year 2017, I can't say that there's any difference across these conferences when it comes to their average attendance, okay? Now, it'll give you a critical value here as well from the F distribution. Now, you have to remember, well, what critical value does this correspond to? Well, I selected an alpha of 0.05, so this would be kind of the 95% critical value. Excuse me, but because it always gives us the p-value, in my honest opinion, just forget about the critical value approach with the F distribution, right? If we're using Excel and we're always interpreting this output, it's way easier to say, is the p-value less than certain alphas? Right? And it kind of shows you what, so here was kind of the numerator for that F statistic. Here was the denominator. It does show you kind of all those intermediate things that I was calculating in the slides, but you don't really have to do anything with them because it's already thrown them all the way through the process, calculated the F statistic, found the p-value for you. That's what you want. You started out wanting to be able to either reject or fail to reject that null hypothesis, okay? Any questions on this? Having trouble with anything? I don't know if you're kind of working along. Okay. All right, so that's kind of our single factor ANOVA. We're just saying, is there difference across kind of groups, or there's one factor here? All right. So what happens if we have data grouped by kind of not just one factor, but two? So we have another ANOVA, right? An ANOVA one. So I love this meme. So we have a two-way ANOVA, which is essentially, well, now I don't just have things that could vary, say, across the different classes I teach, but maybe across the different classes and maybe, I don't know, the, well, what would you call it? Classifications of the students, freshman, junior, sophomore. So I might have two factors that I think are influencing the grades that I see, right? Maybe the course I teach and what year they are kind of in college, right? So another example could be, if I'm thinking about that miles per gallon, well, yeah, maybe I think that there's variation across companies, but there's also variation in the type of automobile, right? So two-way ANOVA is going to provide us two F statistics, right? So one of them would kind of allow us to find a p-value to be able to say, is there variation across the company of car? But the second F statistic would allow me to say, holding constant, kind of the type of car, or sorry, the type of company, does the type of car have any differences in their mile per gallon? Right? So this first F statistic, once we get to Excel, will be, is there significant variation across whatever your row headings are? The second will be, is there variation across your column headings? Okay? So, you know, more technical, what you want to do is create a randomized block design where you only have one observation for each group. Okay? We'll see how you could do this even if you didn't kind of have one observation, but I'll go through, I'll go through both of them, right? So really what you're going to do if you're doing this block design, you would have your original data set. You would then find what the average miles per gallon was for each different combination of make and then kind of model here, or like type of car. Right? Truck, sedan, you know, whatever, however the classifications are. Okay? So that first F statistic, which is saying, is there variation across whatever your row headings are? Okay? So the way that I've written this here is kind of, and actually, I don't have this, I think I copy and pasted. These shouldn't be sample means. These should actually be kind of what the true population means are, right? But what it's saying is, I'm going to assume that if I hold constant this column, right? So the way that I'm writing this, think about this, is this would be the sample mean that comes from some row and some column. Right? So whatever my row headings are, maybe those are like the makes, the different car companies, and maybe the columns are the different types of automobiles. Right? So if I could hold constant that column, is there differences across the rows? So this would be like, if I could hold constant the car company, if that was my column headings, is there variation across the types of automobiles in the average miles per gallon, right? So I assume that there isn't, right? That there is no variability, that they're all the same. and I'm testing for whether or not there is some difference. So if I think about the S statistic for the column heading, what that's saying is hold constant that row, so I'm looking at the same type of automobile, is there variation across the columns, right? Columns 1, 2, and 3. So hold constant the type of automobile, is there variation across the car companies, right? So I can still kind of get at that same thing that ANOVA gave me, but it also allows me now to test for is there variation across this other factor as well, okay? So we've got some assumptions that need to be made. You know, if I am doing this block design, I really should be, you know, essentially every type of automobile and car company would have kind of one block that represented the average miles per gallon for a, you know, Dodge sedans or whatever. Well, I should have the same number of observations for each one of those. In my car example, I probably wouldn't, because I'm guessing some car companies make more sedans, some make more trucks than others. But this is an assumption that we would need. But as a motivating example, the car thing I thought made sense, right? Now, I'm never going to kind of make you kind of check these. I'm going to give you examples where we're going to assume that these things are true. Right? So what I want to focus more on is how do we kind of think about this? How do we do this in Excel? I think we should be able to get through that before we end class today. So let's say I might want to test for whether or not there's kind of a difference in income levels across different racial groups, right? I might be concerned with kind of racial inequality in terms of income. So it seems like a pretty relevant example I could do. But one thing that I also kind of know that really influences income that potentially, you know, because of kind of our nation's history, might vary across different racial groups. One main thing that's going to impact income is education levels, right? So if I have different education levels across racial groups, well then, yeah, of course I'm going to see differences. So what I want to try to do with this kind of two-way ANOVA is say, well, now I can hold constant that row, right? I can hold constant the education level and say, is there variation across races if I held that education level or education attainment kind of the same, right? So it's essentially like looking to see, is there variation across the races if I'm only looking at people with a bachelor's degree? Is there variation if I hold constant, right? If I'm only looking at kind of high school degrees or even kind of no high school dropouts. So I'm able to kind of hold constant this other factor, right? Which I think is also important in terms of affecting income, you know? So I can use Excel to run a two-way ANOVA, and we call this kind of without interaction. So first I would have to construct a table, right? Where I have that block design, right? So each kind of combination of racial category and education level attainment has one block that represents the average income for, say, Asian Americans who have a bachelor's degree, right? I'll just have one number for each one of those combinations, right? So it looks something like this. Now, I kind of like grouped these just so I didn't have as large of a table here. Also, when I tried kind of breaking this down into four, the last category had real small sample sizes, and we really should have similar samples across all these. So I wanted to make sure that I didn't do that. So, you know, if we look at kind of these different classifications for education and kind of these different three kind of racial categories, right? We can definitely see that, right? If I look across these, right? So essentially what I'm doing here is saying I'm only looking at people with a high school degree. Yeah, it looks like there is some variation across the different kind of racial groups, right? As I look at higher levels, I can see, yeah, it looks like kind of across there is some variation, right? But, you know, if I look at here, 38 to 44,000, that's not near as much of the variation I see if I look at, if I hold constant race, how does across education level attainment does income vary? 38 to 108,000, right? So just looking at this data, it looks like there's a lot of variation if I look at kind of hold constant race and look across the educational attainment. And that really exists kind of in each one of these different racial groups. Not quite as much variation, but there still is some variation if I hold constant education and look across kind of races here. Right? So, you know, I calculate these kind of intermediate steps. Excel is going to do this for you behind the scenes, but essentially what it's going to do is it's going to find the average income across the racial groups for only high school degree individuals. Then it's going to find the average for some college, et cetera, et cetera. And then it's going to find the average across all education levels of Hispanic individuals. And it's going to find the average across education of just kind of Black Americans, so on and so forth. Right? So when I have these averages, you can kind of imagine, I'm not going to go through all the math on this one. It's very similar to what all that math I showed you for ANOVA. You could think about, well, now that I have the averages of each race and the averages of every education level, I could somehow look at the variation from the overall average when I'm looking at factor B, which was kind of education level, and I could look at the kind of differences from that overall average from factor A, which was kind of the racial group here. Okay, so we can do this in Excel, right? So, oh, actually, no, sorry, I already did that. I'll show you another example in Excel in just a second, so I'm okay with I'll just keep this example, and then we'll switch to Excel. So it'll give you a bunch of intermediate calculations where it found averages and variances, holding constant kind of the other factor. It then will kind of spit out at you, okay, here's my F statistic and my p-value for the variation across the row headings. Here's my second F statistic, which is the F statistic and p-value for the variation across my column headings. Okay? So if I remember, I kind of have to look back at the data or remind myself, oops, my column headings were race and my row headings, right, were education. Okay? So if I look at my row headings, is there significant variation across in income across educational attainment? Well, the p-value is 0.001. I could say with 99.99% confidence that there, that I can reject the null, which remember, the null was that there is no variation, right? They're all the same. So with 99.9% confidence, I can say income varies across education levels, holding constant someone's race, right? Now, the column F statistic, I can interpret as, well, I can't quite reject the null at the 99% level, right? So holding constant someone's education level attainment, I can't with 99% confidence say that there is differences across the races. Right? But just because I can't say it with 99% confidence, I could say it with 98% confidence, right? My alpha would be 0.02, so my p-value would be less than that. So yeah, I can't say with 99% confidence that if I held constant someone's education level, that there wouldn't be any variation across races. But with 98%, I could say, yeah, there's differences in income across racial groups, even if I hold constant their education level, which seems problematic, right? Like it seems like maybe I should explore this further, okay? Any questions on that? And kind of the way this is literally, I grabbed it right from Excel. So once I show you how to run a two-way ANOVA test, it spits it out at you just like this. So your F statistic for your rows, it'll always kind of say rows, and then you'll have your p-value, and then columns, and you'll have your p-value, okay? Any questions on this? And then, like I said before, right, we just use that if the p-value is less than alpha, we can reject. Right? So I just kind of walked through this. I just said this when I was showing you, but here's kind of a recap of that, right? We could say at the 99% level that we reject the null hypothesis and there is variation across the rows. Can't quite reject at the 99% level, but with 98% confidence, we could say, even holding constant someone's education level, there is variation across the columns, right, or across race. Okay, so what I want to do now, we got 10 minutes, that should be perfect. All right, so let's go back to, there it is. So I've got this GPA data, all right? So I'll show you two different ways we could do this. So I've got GPA data here and ANOVA data with replacement. I was just showing you one kind of without replacement. So to do this block design, right, what I had to do is use this average ifs function. Now, I would, let me see, there we go. right? I could use this block design, run kind of a two-way ANOVA. So I just kind of select this. Right? I'll show you kind of the average ifs in just a second. But what this is doing is kind of finding, is there, what's the GPA for female students who sit in the front row, male students who sit in the front row, female students who sit in the back row, male students who sit in the back row, right, et cetera. So I go to data, I go to data analysis, I go to two-way factor without replication, okay, hit OK. I'll select my input range, right. I selected the labels, so I have to make sure it knows that. And it's going to give me the or the critical values for the 95% level, but it also gives me my p-values, so that's fine. So two-way factor without replication, which was under that data analysis button. Selected my data, made sure I let it know I selected the labels, hit OK. So I look down here, I look at my p-values. So I can definitely reject the null for my rows, which remember, rejecting the null here means that I'm actually rejecting that there's no variation across the rows. So I found significant enough evidence that there is variation across the rows. For the columns, looks like if I were to look at the 95% level, I can't quite reject the null there either. But let's say we just want to do this at the 90% level. So alpha of 0.1, I can reject the null for there being no variation across the columns, but I failed to reject the null that there's no variation across the rows. So if I go back and remind myself of what this is, the rows were where someone sat. So holding constant someone's gender, there's no variation in GPAs based off, sorry, actually, I'm doing this backwards. Did I flip those? Yeah, sorry, the rows, we had a really high p-value. So the rows, we say we can't reject that there's any difference in GPAs across the rows. So holding constant where the student chooses to sit in the class, we can't say there's any differences in the row GPAs, or there's no differences across gender and then the GPA obtained if we hold constant kind of where the person sat. Now, we did see that at the 90% level, I could reject the null for the columns. Remember, the null is that they're all equal, that the GPAs across where someone sits would all be the same. Well, I'm rejecting that. I'm saying I found significant enough evidence where I can reject that they're all the same or that there is variation. Right? So I can now say, holding constant someone's gender, there actually is variation in their GPA based off where they sit in the class, first, middle, or back row. Okay? Any questions on there? Is that clear? So when I was looking at that output, we could kind of rename this as ANOVA without replication output, right? Because my p-value here was so high, I couldn't say that there's any variation across the rows, and the rows were gender, right? But at the 90% level, an alpha of 0.1, I could reject the null and say there is variation across the columns, okay? And I could also do the same thing. I could actually use the critical values and the test statistics, but like I said, it's probably just easier to use the p-values here, okay? Any questions on that? One more thing I want to show you. Excuse me. So I just showed you an example where I did some block design. And that would be important if I did have kind of more males than females, or a few more kind of seats in the front row relative to the back row or something like that, which also I thought this was interesting. If you look at kind of the GPAs of people in the front row versus the back, there is quite a bit of variation. But, you know, any individual that could be different for it. So if I instead had the data set up in a slightly different way, where I have my two kind of factors I think matter, and I have on one side, here's my rows, but I'm actually showing you not just an average for all female students in the front row, I'm showing you here was 5 female students who sat in the front row, here was the 5 female students who sat in the middle row, so on and so forth. So if I had it set up like this in rows and columns, I could then go to that data analysis tab. And now, because I don't just have kind of this block design, this one cell, I can use this two-factor with replication, right? So with replication means that it's going to be going back to the same group more than once, because it's now not just, you know, one single block for each combination. I now have 5 females who are in the front row, right? So I have multiple. So with replication, I'll select my input range. Right? Actually, I can't select my labels in this one, I don't think. So I need to make sure I just select the data. Sorry. So I select the data. Or wait, actually, no. You can select the whole thing. It'll treat these as labels automatically for getting between the different types of tests, right? So I select everything. How many rows do I have per sample? So if I look at kind of female students in the front, I have 5, right? 5 in each of these categories. Same thing for males. So this is one where I need to have the same sample sizes, right? So I can only do this with replication, ANOVA with replication, if I have the same sample sizes across these 2 factors, right? If I had down here like only 4 males in the front or 3 kind of females in the middle, this would be an issue, right? So I then just going to put this on a new worksheet. I'll keep alpha at 0.05. I'm going to look at the p-values anyway, so who cares, right? Hit OK, come down here, and it'll, you know, it spits out a bunch of stuff at you. It's all the intermediate stuff that it was calculating. What you really want to know are, is there kind of variation across the columns, right? And is there, kind of selected sample here, is there variation across kind of the rows, right? So I don't know why it says sample here. You can kind of think about it's going to be rows and columns. I mean, it'll always show you sample, but that represents the F statistic for the rows. Now, with replication treats us a little bit differently because it has a little bit more data, right? It has each individual student that was before being, you know, put into just one block. So you'll notice these p-values change quite a bit, but, you know, or sorry, I shouldn't say they change quite a bit. They're pretty consistent. I mean, at least we'll kind of make similar rejection decisions. I guess for the variation across the columns, right, we found a much smaller p-value, which means that we were really saying we can definitely reject that there is no variation across where someone sits. We found very significant evidence that GPA varies a lot by where someone is sitting, right? But for the rows, we still have a pretty high p-value. So holding constant where someone sits in the class, we're still really not seeing much variation across gender at all, right? So I guess if you're trying to keep this a little bit organized too, ANOVA with replication output, right? Any questions on that? So you might see some of this ANOVA testing done in some of your other upper level courses. I don't particularly like, there's much more valuable tools, I think, in terms of there's so much data out there now that usually we can use something called linear regression to do a way better job of thinking about how something varies, not just across 2 factors, but we can do across, you know, a lot of factors, right? There is a limit on it, but kind of depends on the size of your data. So we'll start talking about that Friday, cover some linear regression stuff, and then do linear regression all of next week, okay? All right, the online quiz will be posted when I get done with my other class. I'll also get that Connect assignment and that individual assignment. You can kind of start working through that individual assignment at least, and then after Friday and next week, chip away at that Connect assignment. All right, I'll see you guys on Friday.
What's the due date on both?